Hello class, as I told you in the previous lecture as well that one of our lecture for this course will be in the asynchronous mode. That is, I will send you the recording of the lecture on YouTube or Microsoft Streams as well. You can watch this recording for this lecture, and at the end, if you have any question, you can ask me. Actually, this topic is not very complicated and it involves some simple theories or some simple formulas or criteria to judge whether a material will fail or not. So it wasn't necessary to do this in the live session or to do this via live interactive session. So I thought it's better that I will send you the recording and you can listen to it later on. If you have any question about this lecture, you can ask me in our class groups at different forums. So let's start this lecture. Actually, you are well aware that the ductile material is the one which undergoes large deformation before it finally fails. Now, this phase of deformation or is known as yielding, as you already know that any ductile material, for example, even the steel material. Steel is a kind of a ductile material which undergoes large deformation. If you plot the elastic curve, it will be a stress strain curve for this material. It will be something like this. That after this point, or when the yielding occurs, the immediate failure will not occur. It will undergo large deformation, and that portion is called as the warning portion, you can say, where the material will give you more warning. For example, in a house construction or in a structure where steel is being used, it will undergo large deformation before finally it will fail. But in contrast, there is a brittle material as well, which will fail abruptly. It won't deform at all. And whenever the load approaches the ultimate strength, it will immediately fail. So it doesn't give you that safe passage or warning before failure to evacuate a building. So this is basically the difference between a ductile and brittle material. And that is the reason that while we are designing some structure in which ductile materials are used, we would consider the yielding stress as the failure criteria. Although in this type of material, in the case of ductile material, it will undergo large deformation even after the yielding load. For example, this yielding stress will occur somewhere over here, and even after this yielding stress, it will take some stress or some load. But we will consider this yielding stress as our failure criteria just to be in the just to be on the safe side. But in the case of brittle material, the failure is specified by fracture or stresses at the fracture. For example, in the case of failure brittle material, the failure or elastic stress strain curve will be something like this one. It will take some load and then immediately fail. And this point or this load is called as fracture load or fracture stresses. So we will take this as the criteria of failure or the limit of failure or the maximum stress that this material can take. Although these criteria are true only if only when the case is that the material is subjected to uniaxial state of stresses. For example, in the case of steel material, we usually apply the load in one direction due to which this yielding stress is produced, and that yielding stress we will take as the failure criteria. Similarly, in the case of, let's say, concrete material, we usually apply the compressive stress, or by compressive stress, it means that we are applying the uniaxial stress, the stress in one direction only. And based on this compressive load, we calculate the fracture stress, and this fracture stress is taken as the failure criteria. So, but it is not always the case. Although in most of the cases, it is true that only the load in one direction is acting. But what if the material is being loaded in different direction, or if biaxial or triaxial stresses are occurring in the material? Then the criteria of failure becomes different. In the uniaxial state, the criteria is simple that in the case of ductile material, if yielding occurs, material fails, and in the case of brittle material, if fracture occurs, the material fails. But in the case of biaxial stresses, when there are different stresses occurring in different direction on the material, then what is the criteria, or what should be the criteria of failure? So for that case, or to figure out the criteria in that case, we have different theories of failures. which have been proposed to predict the failure of materials subjected to multiple state of stresses, right? And why there are different theories? Because one theory is applicable or may be applicable on one type of material, and each material cannot behave in a single manner. For example, a material may fail or material may behave like a ductile material or a material or a brittle material, depending on the type of loading, chemical conditions, temperature, or even fabrication, that how it is being loaded and what is the length and what is the correlation between type of load and length. So such type of factors influence that whether a material will behave as a ductile material or a brittle material. But the basic procedure to determine the to determine the which theory is being applied or which type of failure will occur is same in all these type of material. The first step is to calculate the normal and shear stresses that you know are sigma x or tau xy. So first, for every type of material we have to calculate these stresses. Then based on these stresses we will calculate the maximum normal and shear stresses, that is sigma 1 or sigma 2, and also tau xy, or we can represent as tau 1 or tau 2, that is maximum normal and shear stresses. And based on this maximum principal and shear stresses, we will apply these theories of failure to figure out whether the material will fail or not. So let us just discuss these theories. So the first theory that was proposed by Rankine was the maximum normal stress theory. According to his theory, it was assumed that the failure will occur when the largest principal stresses equals the ultimate stress of the material in the uniaxial test. Now you know that any type of, for example, let's consider a beam structure on which a load is acting, something like this one. And for this material, we can calculate sigma x and sigma y, as you already know from our stress transformation or stress calculation lectures pre-midterm. So for this material, let's suppose that this is sigma x, sigma y, this is tau xy at, let's say, any random point. Now for these sigma x, sigma y and tau xy, we can calculate sigma 1, sigma 2. There will be an element which is oriented at some angle on which these stresses, these normal stresses and shear stresses are maximum. And those stresses are called as sigma 1, and let's say this one is sigma 2. Now Rankine proposed that the material will fail when the largest principal stresses. Now we have two stresses, sigma 1 and sigma 2. So this theory is quite simple, that he proposed that the material will fail when the largest principal stress is out of these two. Let's say if sigma 1 is largest, then he said that if the largest principal stresses is equal to the ultimate stress of the material will fail. Okay, so when the load is being applied, these normal and shear stresses produced. Due to these normal and shear stresses, these principal stresses are being produced, and when these principal stresses approaches the ultimate stress or becomes equal to or greater than the ultimate stress, then the material will fail. Similarly, if sigma 2 is the largest principal stress, then when this sigma 2 or the absolute principal stress will become equal to or greater than the ultimate stress of the material, then the material will fail. So this is the basis of this normal stress theory which was being proposed by Rankine. So now we have two conditions to satisfy. In these theories of failure, there is a unique way to represent the mode of failure. For example, now we have two conditions to satisfy. One condition is that sigma 1 is equal to sigma ultimate. When this condition is satisfied, the material will be failed. And the second condition is that when sigma 2 is equal to sigma ultimate, then the material will fail. Obviously, it is a simple case. You can calculate the sigma 1 and sigma 2 and simply compare it with sigma ultimate, which is different for different type of material, and you can say whether the material will fail or not. But in next theories, you will see that we will have some complex equations, and it won't be very convenient to figure out or to check this relationship. So in order to avoid this confusion, they have just simplified it briefly. For example, if I take this sigma ultimate on this side, I will have this equation that sigma 1 over sigma ultimate is equal to, it can be plus minus 1, because this sigma ultimate can either be in tension or either be in compression. Similarly, this sigma 2 can be equal to sigma ultimate is equal to plus minus 1. So we have two conditions. If these two conditions are satisfied, then the material is safe. But if these two conditions are not satisfied, then the material is going to fail. So to represent these two conditions in the graphical form or in the graphical manner, it is something like this one. For example, sigma 1 over sigma ultimate can be equal to 1. We have 4 points, that is sigma 1 over sigma ultimate. If I represent these two conditions in a graph, that will be sigma 1 over sigma ultimate is equal to plus 1, which will be this point, right? And the other point is sigma 1 over sigma ultimate is equal to minus 1, which will be this point or this line over here, right? And the third point is sigma 2 over sigma ultimate is equal to 1, which will be this point or over this line, right? And the fourth condition is that sigma 2 over sigma ultimate is equal to minus 1, which will be this line. Now, what will you do when you are solving the problem? You simply have to compute sigma 1 and sigma 2 and plot in this graph. We have this graph and you will plot this one. And let's suppose that the point of sigma 1 and sigma 2 is lying somewhere inside this graph. So if the point is lying inside this graph, that means that the material is safe and it won't fail. But if the point sigma 1, oh sorry, we have to calculate this sigma 1. You will calculate sigma 1 and sigma 2, then you will calculate this ratio sigma 1 over sigma ultimate and sigma 2 over sigma ultimate, right? And then you will plot these two coordinates in this one. If these coordinates are lying inside this graph or inside this square box, then the material will not fail. But if they are lying outside this plane or outside this box, then the material is going to fail, or we can say that the material will fail whenever this kind of stresses or this much sigma 1 and sigma 2 stress will occur. So this is one theory, that is maximum normal stress theory, and this is its failure criteria, and this is its explanation that what is the criteria being proposed by Rankine. But again, there is one limitation of this theory, that in this theory, although he has proposed that the maximum principal stresses should be equal to sigma ultimate for the failure to occur, but he didn't consider, or he assumed initially, that this sigma ultimate or the material has the same strength in the tension or compression. He has not considered these tensile stresses or compressive stresses separately. For example, if there is a material, let's say if this is a concrete block, then obviously it will have some strength in the tensile or when the tensile loads are acting, and it will have some strength when the compressive loads are acting on the material. But in this theory, it was assumed that the strength of a material is same in tension and compression. So that is why this theory is not applicable for all type of material. And another point that I forgot to represent, that these theories that we are just discussing are applicable for the brittle material which can fail, which fails abruptly. This maximum normal stress theory, and the second theory that we are going to discuss about the brittle material is this MOS theory. Now this MOS theory is used for material that have, so it has addressed the limitation of that previous Rankine theory, that was that the material has same strength in tension and compression. So the Mohr's theory proposed, so Mohr basically proposed the theory for the material which have different properties or different stresses or strength in tension and compression. So it has taken into account both the factors, the tensile forces and the compressive forces. So he proposed that initially to apply this theory on any type of a material, let's say if this is a steel bar on which we want to apply this Mohs theory, we need to know that what is its strength in tension and what is its strength in, let's say if this is tensile strength, and what is its strength in compression. So he basically proposed a unique theory. For example, if there is a material, let's consider this figure, on which we apply, let's say this is a steel bar, on which we apply the tensile load, and based on this tensile load, we will get its ultimate strength in tension, right? And similarly, when we apply the compressive load on this one, we will get its ultimate strength in compression, right? So for any material, the tensile strength and compressive strength will remain constant. Okay, so he basically said that we need to know these tensile stresses and compressive stresses. So when we know these tensile stresses and compressive stresses, we will plot the Mohr circle for these stresses. So when the tensile force was acting on the material, this force was acting only in one direction, that is this y direction, let's say. So the other stress is equal to 0. So the stress will be produced in one direction only, that is this sigma ultimate tensile. So considering this origin as the starting point or point 1 of this Mohr circle, and this tensile stress as the maximum stress of the circle, we will plot this Mohr circle. And similarly, we will plot the Mohr circle for the compressive strength. This is the compressive stress, and it is being plotted on the negative sign because initially or in our calculations, we are always taking the compressive stress as negative. So we will plot the Mohr circle for this compressive stress. Now, these two Mohr circle or this figure is applicable for one type of material, because for every material we have different tensile stresses and different compressive stresses. So now Mohr said that you will first plot these tensile stresses and Mohr circle for these tensile stresses and compressive stresses. And after plotting these Mohr circle, you will connect the tangent of these Mohr circle by this line over here. Similarly, below here, you will plot this Mohr circle. And now you have this one figure which is applicable for one type of material. Now he said that now after you have got this figure and you have, let's say, some force that is acting on this material, some random force, right? Based on this random force, you will calculate sigma x and sigma y for this material. And after getting this sigma x and sigma y, again you will calculate sigma 1 and sigma 2. When you have got this sigma 1 and sigma 2, you will plot the Mohr circle, let's say for sigma 1 first. For example, if the Mohr circle for sigma 1 is something like this one, that is lying inside these two limits or inside these two tangents, then we can say that the material is safe and it is not going to fail. But again, if this, let's say, Mohr circle for sigma 2 is something like this one, or it is going outside these two tangent points, then we can say that the material is going to fail. So for the Rankine's theory or the maximum normal stress theory, our failure block was this square element. But in the Mohr theory, our failure is these two circles which are being connected by the tangent line. Okay, so this is the basic difference between these two theories which are applicable on the brittle material. And another thing that Mohr considered, initially he proposed the theory for the two types of stresses, that is when the material is under tensile and compressive stresses. But he said that this theory can be modified, and if we can figure out, because obviously shear stresses can also occur. So material can have a strength in shear direction as well. So he said that if we can figure out the shear stress of the material, let's say the shear stress after the Torian test or by doing the Torian test comes out to be this tau xy, right? So he said that if we plot the circle or Mohr circle for this shear stress as well, which will have a radius from this center to this point that is equal to tau xy, okay, so this is the radius of this shear stress circle. And if we plot this shear stress circle, now we have three circles because we have considered three separate strengths of the material. And if we plot a tangent that is passing through these three circles, then this will be our criteria for failure. And again, we will calculate this sigma 1, sigma 2, and again we will plot these circles inside. If the circle is completely inside these tangents, then the material is safe. But if the circle goes outside this three circles or these two tangents, then the material is going to fail. So this is how the Mohr's theory of failure works.